What you see in front of you here is actually the formula to calculate the ppm or delta units on the NMR. Notice it's equal to the distance downfield from TMS in hertz divided by the operating frequency of the NMR in megahertz. Remember, as I mentioned before, different NMRs operate at different frequencies, which means if you use a given NMR machine to run a certain spectrum, the distance downfield from TMS in hertz will be a particular value. But let's say you put the same sample in a different NMR that operates at a different frequency, the peaks are not going to be the same distance from TMS in hertz, which means scientists using different NMR machines would end up with two different sets of data for the same molecules. This would be obviously not very smart. So that is why they developed the ppm or delta unit. Notice the formula takes into account the distance downfield the peak would be from TMS and the operating frequency of the machine. So if I run a sample in my NMR and I get a peak at around 1.2 and you have a different NMR but ran the same sample, you would also get a peak at 1.2. It's this formula right here that also happens to give rise to these very valuable charts. You'll find something like this in your Orgo textbook. Notice on the first line here it's saying that methyl protons peak at around 0.85 ppms. And all the way down on the chart, protons of an alcohol would peak at around 2 to 5 ppms, and it's variable. Some professors give you charts like this on your exam and some don't. It's something that you're going to want to ask your professor, because obviously this chart would be very valuable on an exam. But just in case if your professor doesn't give you this chart, you should have a rough idea where hydrogens peak on the NMR. Notice this chart goes from 0 on the right all the way to 12 on the left. Typical alkane hydrogens right here peak at around less than 1.5. You'll notice right here this is an allylic hydrogen. They would be slightly more shifted because they are in proximity to a double bond. Hydrogens right here on a carbon that happens to have X, that being some kind of halogen, would be even more shifted. But notice hydrogens on a carbon that are doubly bonded would be even more shifted. So notice double bonds have a greater shifting effect than halogens. And we also saw before hydrogens on benzene rings would be very shifted. But notice these remaining hydrogens over here, they are literally off the chart. They can peak almost up to 12. You don't have to memorize this, think about it. These hydrogens are not only next to a multiple bond, but they're also next to electronegative atoms. They're next to the two things that cause hydrogens to be shifted. So what's it all about here? Second aspect of NMR. That is number 2 here, proximity to an electronegative atom and or multiple bond causes a peak to be shifted more downfield.